Spectroscopy. 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 What is it? How do you actually pronounce it?
Spectroscopy.
Why is your microwave called that? What does Pink Floyd's Dark Side of the Moon and a bunch of lines have in common? Why don't we find out together?
Here we go!
Hi there, my name is Alistair. I go by he, him, its, and all neo pronouns. I have no credentials other than a food handler's card that expires in about 6 months. Shout out to retail management operations in senior year of high school for that one. I am very clearly the authority figure on spectroscopy and just astronomy as a whole, now that you know that. So why don't we dive into my buddy, spectroscopy. ATA Science describes spectroscopy as the study of absorption and the emission of light and other radiation by matter. Starlight creates color. It is in this color that we see different lines, and in these lines we can tell what a star is made up of elementally. It is through all of this that we can then classify stars accordingly.
Ooh, we've got
The electromagnetic spectrum. The electromagnetic system is the toolbox for spectroscopy. It lays down a lot of the groundwork for what astronomers have to work with. The electromagnetic spectrum itself is made up of different types of light and radiation, and each area on the electromagnetic spectrum represents a different type of this light or radiation. Gamma rays are produced by the hottest and most energetic things in all of the universe. X-rays are produced by things like the sun's corona, which is the outermost layer of the sun. The sun also produces ultraviolet rays, UV rays. It's the reason we have to wear sunscreen when we go outside. Humans can't see this, but many insects, like bees for example, can. After this, we have visible light. It is what we can see, its colors. Then infrared light. We can't see this, but we do detect it as heat. Microwaves is something that I kind of struggled with finding my own definition for, so we'll see what NASA has to say. Microwaves are a portion or band found at the higher frequency end of the radio spectrum, but they are commonly distinguished from radio waves because of the technologies used to access them. So your microwave is called a microwave because to microwave your food, they use microwaves to microwave your microwavable food in the microwave. Yeah. After that is radio waves. And radio waves have the longest wavelength of any of them. So, you may be asking yourself, how does this relate to spectroscopy? How is this the toolbox and the groundwork for a lot of it? Well, X-rays and ultraviolet light can cause transition in atoms and molecules, leading to emission or absorption of specific wavelengths. Visible light produces color and can be absorbed by certain materials, leading to spectral features that are characteristic of those materials. Infrared radiation interacts with molecular vibrations and rotations, providing information, bars, about molecular structures and chemical bonds. Radio waves can be used to understand the energy levels of atoms and molecules in a magnetic field. Through the ways that stars interact with radiation, particularly light, across the electromagnetic spectrum, astronomers can classify stars accordingly. Astronomers use telescopes to collect light from stars, which is then directed into a spectrograph to be analyzed. The light is dispersed and the lines show up depending on the types of spectra. There are 3 types of spectra that an astronomer will use to classify a star: continuous, absorption, and emission. If incident light contains more photons while wavelengths, like blackbody radiation for example, the light will disperse into a continuous spectrum. This spectrum won't have any lines at all in it. It will just be a rainbow the whole way across. There is nothing blocking the light from passing through it. This allows for all wavelengths to smoothly get right through. An absorption spectrum shows dark lines called bands at certain wavelengths to show the light that has been absorbed by the elements, and this in turn shows us what a star is elementally made up of. The emission spectrum shows no rainbows, but it does show colored lines. So this will be a black box across with different colored lines in it. Emission lines are produced by low-density gas and can only occur at certain wavelengths. Absorption and emission lines are used to infer the presence of chemical elements, molecules, and compounds in distant objects like stars. They also use these compositions to determine the velocity of an object in comparison to Earth. Objects will appear either blue shifted or red shifted. Blue shifted objects have a frequency that is increasing, and these objects are moving closer to us. Red shifted objects are the opposite. They're moving away from us and have a decreasing frequency. So, in short, continuous spectra have no lines, just rainbow. Absorption spectra have dark lines, and emission spectra have colorful lines. If a spectrum has a few strong lines, then it's a hot star. If there are many weak lines, then the star is sun-like. On the rare occasion that there are a few or no lines, it indicates that the star is simple in composition. Not all stars have the same spectrum, of course, but they can be grouped into different classes. Only bad astronomers forget generally known mnemonics. That's the way to remember the Morgan-Keenan star classification system. From hottest to coolest, the groups are O, B, A, F, G, K, M, with brown dwarfs at L, T, Y. Within those groups are subgroups from 1 to 9, with 1 being the hottest and 9 being the coolest. For reference, the Sun is a G2 type star. At the most extreme ends, the O stars are from 25,000 to 55,000 degrees Kelvin, while M-type stars are less than 3,600 degrees Kelvin. The hotter the star, the closer to O that it will get. Brown dwarfs are objects cooler than about 2,500 degrees Kelvin and can't sustain nuclear fusion. They have their own classification and won't cross into O, B, F, G, K, M. Spectroscopy is the study of light and radiation and how it interacts with matter. Light will disperse through a prism or a spectrograph showing lines and therefore indicating what a star is chemically made up of. And then from there, we can classify it. So anyways, thank you for watching the video the whole way through. I hope you liked it. If you didn't, I hope it was informational enough to give me full credit and an A, plus maybe if you're feeling generous. Yeah, anyway, thank you so much for watching, and
Bye-bye.